Okay, so a couple of things here, guys. Reminders for this week, things that are coming up. Okay, your energy conversion lab reports are due tomorrow, right? And that is the last like kind of homework activity. We're going to be starting something today and working on it again tomorrow. That is just an in-class activity. It will not be for homework because you will get it done in class between today and tomorrow. Okay, and then that will be the very last thing you hand in for marks, other than your unit exam, which, reminder, is coming up on Wednesday for Unit 3, okay, and then June 14th for this last unit, which is obviously quite short, okay. Reminder that your final exam is June 22nd, and it's in the morning at 9 a.m. I don't know which room that is in yet, but probably this one, okay. They usually try and get you to write your finals in the same room you had the class, if at all possible, so probably be in this classroom, okay? But I'll let you know as soon as I know where that exam location is. All right, so Unit 4. Okay, Unit 4 is about, it's kind of a hodgepodge actually. It's kind of a little bit of everything. There's some energy and thermodynamics. There's a little bit of chemistry. There's a little bit of biology. Okay? It is matter and energy in global systems. So we're kind of looking at how all the technical stuff we've talked about throughout this course works in a global system. Okay? How does energy get transferred around the Earth? Okay? How does that affect living organisms? What's the kind of the chemistry of that, of those interactions? Where does the chemical energy come from? Where does it go? Okay, all of that kind of stuff. So it's supposed to kind of tie everything that you've learned together, right? But like I say, it's a pretty short unit. That said, because it's a very short unit, the unit exam is a really good opportunity to boost your mark right before the final, because there's not very much stuff on it, okay? So you don't have to be a master of a whole bunch of material for this unit. It's just a small amount of stuff, okay? So it's much easier to kind of prepare and be ready for that unit exam. All right. Okay, so what we're going to talk about today is climate. Okay? And we're going to look at the components of that, the factors that affect climate, and then we're going to look at analyzing climate graphs and charts and get started on an activity about doing just that, analyzing climate graphs and tying that into factors that affect climate. Okay. All right. So components, factors affect the climate on plants, animals, and humans. Looking at inputs and outputs of various environments. Okay, and understanding climate graphs or climatograms. Okay, is what we'll be looking at today. All right. If I was to ask you what climate is, what would you say? Give me an idea of what they think climate is. There's not really a wrong answer.
Weather in a certain habitat area.
Yeah, the weather in a certain area. The prevailing weather, okay, in a certain area. So when we talk about the climate here in Okotoks, right, we would describe what the weather is like here. Now, when I look at the weather in the morning, so I pull up my phone and open up the weather network or look at the weather app or whatever, okay, and I look at it, there's probably about 4 things that I'd really be concerned about in the weather. Okay? What would those 4 things be? What would I want to know about what the weather's going to do today? Exactly. I'd want to know what the temperature's going to be. Okay, what else? What's that?
What it actually feels like.
Yeah, what it might actually feel like. Okay, what else?
Humidity or precipitation chance.
Yeah, chance of precipitation, what kind of precipitation, how much humidity there would be. Wind, yeah, I mean, especially around here. Right? It's been an exceptionally windy year, right? So we would want to know whether we're going to be getting those winds that blow your barbecue off the deck, okay, or whether it's going to be nice and calm. All right, and what else? Probably wouldn't always think of this, but it's something that's always on there, and it changes throughout the year.
I guess it would be visibility.
Okay, it's related to visibility. Visibility kind of tells me how cloudy it is, which would certainly be something I'd be concerned with.
Light.
Light. Okay. we're coming up on the longest days of the year. Okay? And the more hours of sunlight we get, the more solar energy comes in, the hotter the weather gets. Okay? And then obviously back around Christmas time is around the shortest day of the year. Okay? We get very little low angle sunshine. Okay? Those are the components of climate: temperature, precipitation, light, and wind. Okay? Those are the things that influence the weather most, okay, or are part of the weather, okay, in a certain location. All right, so climate is the prevailing conditions, weather conditions at a location, and these are the major components. This sentence is super important. You need to know these 4 components. This is what makes up the weather, or makes up climate. So the key word in the definition of climate is prevailing. What does it usually do? Okay, so when we're talking about the climate of an area, we're talking about the prevailing weather at that particular time in that particular location. Okay, people get this idea that climate is an average of the weather, right? Which isn't true. Because if I described the climate here in Okotoks with the average numbers for temperature, precipitation, light, and wind, this is what it would sound like. The temperature in Okotoks is about 6 degrees Celsius. There's 12 hours of daylight and 12 hours of night. The wind is out of the southwest at 30 kilometers an hour. Okay? And there's a chance of getting about 0.5 millimeter of precipitation. Okay? That would be the average numbers. Okay? If I looked at the weather we get over the course of an entire year and just averaged it, that would be the average weather. But that's not how we describe climate. That's not an accurate description of what it's going to do on a day-to-day basis here in Okotoks. Okay? Because the weather changes around here. It's not like Hawaii. Okay? Being a meteorologist in Hawaii is like the best gig ever. It's the same weather every day. You can set the whole week and walk away. Okay? It's going to be about 30 degrees. There's going to be some wind in the afternoon, some showers in the evening, and the next day we'll start all over again. Okay? That'd be great. Okay? In Alberta, being a meteorologist is much tougher. Okay? That's why we have the saying, if you don't like the weather, wait 5 minutes. Okay? That's why people like Leonardo DiCaprio think that they witness climate change when they come here. Okay? Because they don't understand what Chinooks are and how quickly they can change the weather, not climate. Okay, you have to, this is now, after today, you will officially, you probably already are, but you will officially be smarter, okay, than Leonardo DiCaprio, because you'll understand that climate and weather are 2 different things. Okay? Climate is the prevailing weather. Okay? Weather is what it's doing right now. Okay? And that can change. And here in Calgary and Okotoks, it can change pretty quickly. Okay? We can have a 30-degree swing, okay, in temperature in one day. It doesn't happen very often, okay, but it can happen. Okay? Chinook blows in and that's it. Okay? It can go from -20 to +10 just like that. Okay? And the wind will come up and it'll seem like the world's going to end. But that's what it's like around here. Okay? Everybody else says you can't have all 4 seasons in one day. Alberta says, hold my beer. Okay? Because we can do that. Okay? We can have all 4 seasons in one day. Right? It's crazy here. Okay? Climate is much different here. Right? Weather is much different here. All right, so if I was going to describe the climate for Okotoks correctly, okay, I would say that at this time of year, okay, we get a lot of daylight, okay, somewhere around 15 hours. We get warm temperatures, usually in the low to mid-20s. Okay, and June is the wettest month of the year. We can get 70 millimeters of rain in June, sometimes more. June is our wettest month. July is the second wettest. Okay? And then it kind of tapers off pretty fast after that. We get most of our precipitation in about 6 or 8 weeks. Okay. All right, questions on the components of climate and what climate is? Okay. All right, now, this would be one particular day, this picture. It shows that the weather in an area is an interaction of these components. Okay? If we're going to get clouds like this, what kind of cloud is this? See if you remember your grade 5 science. Has a big long name. Cumulonimbus, right? This is a thunderhead. Okay, this is what we get, okay, in the summertime. We're coming up on kind of thunderstorm season, right? We get these big, tall thunderheads that build throughout the day, right? In order for these to build, certain conditions have to be present. It takes a lot of energy to build a thunderstorm, right? Which is why we typically only get them in June and July, sometimes in August. Okay? There has to be a lot of energy. There also has to be a lot of moisture. Okay? So we're talking temperature, we're talking light, okay? We're talking precipitation. This is going to cause precipitation in some form or many forms. Okay? Could be rain, could be hail. And obviously it's going to generate some wind, because creating a thunderhead usually involves a rapid destabilization of pressure. And when there's a massive destabilization, you get very strong winds trying to equalize the differences in pressure. Right? So if you didn't know, here's how a thunderstorm builds. Okay? In the early parts of the day, hot air full of moisture begins to rise. Okay? So water is evaporating from the surface of the earth, okay? And it's rising. Okay? As it goes up, it reaches a point where it gets cool enough that it condenses back into liquid water. If the conditions are right, there is so much warm, moist air moving upwards that the water droplets can't fall back downwards. They're actually pushed back up, and they're pushed higher and higher and higher. So they actually go through a cycle. They go up, and then they try to fall back down, but there's so much of this warm air pushing that they get pushed back up. There it is. Okay, into the cloud, and then it keeps building, and so on and so on. And you notice throughout the day, a thunderhead gets taller and taller and taller. Okay, they start to look really dangerous when they start flattening on the top. Okay, that's when you know it's going to get bad. Okay, if they start to get flat and kind of fuzzy as opposed to puffy, okay, on the top, then you know you're way above the freezing point of water. So these water droplets, they go through this cycle. Each time they go through this cycle, they get cooler and bigger. Eventually, they get past that point that they're drawing here, the 0 degrees Celsius point, okay, and they start going through that cycle, but they don't ever fall below the point where the temperature is above freezing. So now, the moisture that's moving upwards condenses onto the piece of ice and makes it get bigger and bigger and bigger. All right? So if you ever, next time it hails, it's not like it's never going to hail again, okay, but the next time it hails and we get the big ones, grab one. Wait till the hail's done. Don't go out in the hail to get one. Okay? When the hail's done, go out and get one and just break it. It looks like an onion on the inside. Okay? Because it's made by having this process happen over and over and over again. The more times the hailstone goes through this cycle, the bigger it gets, because each time it goes through it, water condenses and freezes onto the outer layer, making it bigger and bigger. Okay? And they can get, we know golf ball size is not uncommon. Okay? We can get, baseballs, softballs. Okay? I think the largest one ever recorded was the size of an ice cream pail. You can imagine about 3.5, 4 liters worth of water. Okay? If that thing hits your house, it's coming right through the roof. Okay? Pretty big. Right? Biggest ones I've ever seen were softball. So, like this. They had those in Wainwright in 2003. Every single car dealership in the town wrote off their entire inventory. Okay? All those cars sitting out, and they get hit by softball-sized hail, you can't fix that. Okay? Windows are broken, like roofs are caved in, dented beyond. They were sold for parts. Okay? And none of them body parts. Okay? All engines and stuff that didn't get wrecked. Okay? So the more times it goes through, okay, the bigger it gets. There's actually a urban legend kind of story, but it could be true, okay, of a bomber pilot in World War II who jumped out of his plane and opened his parachute in a thunderhead and actually went through the cycle and came down in a block of ice. Right? Theoretically, that could be true, especially if the parachute opened, okay, and you've got this big updraft. It would be enough force. If it's enough force to hold hailstones up, if you've got a big parachute open, it'd be enough to lift you. Theoretically, it's possible. Whether practically something like that would ever happen is another question, but it's a neat urban legend to see somebody come down in a big hailstorm. It's a little weird. It's also rained frogs and fish before. That's actually a true story. Okay? If you get a tornado, goes over a lake, something like that, or over a swamp, it can pull up all the stuff that's in it, and then when it kind of peters out, all that stuff falls. Okay? So like go rain frogs or fish. Okay? In certain places, weird but true. Okay, so there's a lot of energy involved in all of this, and that's an interaction of the right set of factors. Okay, pretty common set of factors in the summertime, right? This spring slash winter, okay, we actually had one of the rarest forms of weather. Anybody know what it was? Like meteorologists wait their entire lives to see one. A thunder flurry. Okay? A snowstorm with thunder and lightning is incredibly rare because you have to have just the right interaction of factors. Normally in the winter, there isn't enough energy to build a thunderstorm. But if you get the right kind of air inversion with a lot of warm air over top, okay, you can actually get one of these to build, and then you get thunder and lightning and snow. Okay? It's incredibly rare. Okay? If I can find the YouTube video of the retired meteorologist running around like a crazy person cheering about seeing one for the first time, I'll show it to you. I'll have to find it, but it's pretty cool. Yeah. All right. Now, things that can affect your climate. So those are the 4 components. We don't want to get them confused here. Okay, but what we're going to talk about now are the factors that make your climate the way it is. Because obviously the climate here is different from the climate in Oregon or Egypt or wherever, right? Like climate is based on where you are, and where you are brings different factors into play. So the number 1 factor affecting the climate of an area is latitude. Okay? So if you ever get a question that asks, what are some factors that affect the climate of an area? Write latitude, because latitude affects everybody. Okay? Where you are on Earth affects your climate because it affects how much solar energy you receive. Okay? So if we're looking at the Earth, and it's actually oriented this way, okay, perfectly straight up and down. How many days a year is the Earth actually oriented perfectly straight up and down? One's in March, one's in September. Anyone know what they're called? Those are the 2 days, September 21st and March 21st. Starts with E. Equinox, yeah. Okay? The equinoxes are the 2 days of the year where the Earth is actually perfectly straight up and down relative to the sun, because the Earth's axis is actually tilted 23.5 degrees. Okay? So as the Earth orbits the sun, okay, and goes around the sun, let me see if I can do an approximate. Hang on, I gotta orient the board here. Yeah. That's why. So the reason we have seasons is actually due to the fact that the Earth's axis isn't perfectly straight up and down all the time. It's tilted. Okay? It has nothing to do with the fact with the Earth getting closer to the sun or further away from the sun, even though that also happens. Okay? The Earth's orbit is not a perfect circle. It's somewhat elliptical. Okay? And it's enough that the Earth is actually significantly closer during certain parts of the year. Actually, winter for us, okay, is when the Earth is closest to the sun, okay, and we're furthest away in the summertime. It's not enough to make a huge difference, okay, but it makes a bit of a difference. But that's not what causes the seasons. What causes the seasons is the fact that if here's the sun, okay, and the Earth, this is the Earth's orbit, so the Earth is going to go around like this, okay, we're looking at it from the side, okay, there would be 4 points we'd be concerned with, okay. This, and this. Okay? So, as the Earth goes around the sun, its axis is tilted, but it doesn't change. Okay, the Earth's axis actually does wobble over time, but okay, for all intents and purposes, it does this. So as the Earth goes around the sun, this point and this point, the Earth is essentially perfectly straight up and down. These are the 2 equinoxes. Okay? This is when the axis is tilted this way. So this is the North Pole, this is the South Pole. Okay? So, the one on the right, winter or summer? Winter. winter. Okay, here's why this one's winter. We're tilted away from the sun here. Okay, so remember, the sun's light hits the earth, okay, and it hits it like this. All right, so this would be day, this would be night. As we spin around on the axis, we don't end up in the sun very much. That's why the days are so short. Okay, because we're located, you know, kind of right here, so we don't spend a lot of time getting into the sunlight. So the days are really short. We're only in the sun for 6 hours. If you're in the Arctic Circle, okay, you never see the sun. Okay, it's dark all the time because you're tilted away and you never rotate into the sun's light. This is summer. Okay, in the Arctic Circle, they're pointed toward the sun 24 hours a day. Anyone ever been to the Arctic Circle in the summertime? It is the weirdest thing. The sun does this. It makes a circle overhead. It never sets. Never rises, never sets. It just does this overhead. Okay? Because you're pointed at it instead of up and down. Right? Because what makes the sun rise and set is that you turn and face it and turn away from it. Well, in the summertime in the Arctic Circle, they're always pointed at it, so it just does this. Right? I don't know if you guys have noticed this, but you probably won't be able to unsee it now. Okay? But in the wintertime, the sun sets like over there, or sorry, rises over there, and sets right over there. It makes this pathetic little arc, okay, across the southern sky. Right now, the sun rises over here, okay, and sets way over there. We get way more overhead, directly overhead sun, because we're tilted towards the sun. Okay? So it gets warmer because we're A, in the sun more often, and B, more directly facing the sun. Okay? Here, we're facing the sun, facing away from the sun. So even when we're in the sun, we're not getting very direct sunlight. Right? So this is the effect of latitude. So looking at this diagram here, if I'm at the equator, right? So, or in an equatorial area, and I get a certain amount of sunlight, that sunlight is concentrated on an area this big. Okay? As I move further northwards, because the Earth is round and tilted, okay, that same amount of sunlight, okay, is now covering a bigger area. So is it as intense? It's not, and it gets worse. The further north you go, that same amount of sunlight is covering an even bigger area. Okay? Now, when it's summertime and we're tilted like this, we're more like down here. So we get more intense sunshine because we're tilted towards the sun. Okay? In the wintertime, we're tilted this way. Okay? It's more like up here, and it would be way worse. Okay? So that's why latitude affects your climate. The closer to the equator you are, the more directly overhead and the more intense your sunshine is. Okay? In fact, between 23.5 degrees north and 23.5 degrees south, okay, essentially the amount of sunshine received doesn't change throughout the year. They wouldn't use daylight savings time in a place like that, okay, because they wouldn't have to. Right? The sun's intensity really doesn't change very much. Questions on the effect of latitude. Right? So the further away from the equator you get, the less intense your sunshine is, and that obviously affects your temperature. Okay? All right. Second factor affecting climate, and this can also affect any place on Earth, is your altitude. Okay? The higher up you go, the thinner the atmosphere becomes. The thinner the atmosphere becomes, the less able it is to retain heat. Okay? The thicker the atmosphere is, the better it retains heat. So the thinner it gets, the less ability it has to maintain and retain heat. Which is why we see snow on the mountains, even though there's no snow here. Okay? We're at a much lower altitude. We're at exactly the same latitude. We look across at the mountains, that we know they're the same distance from the equator that we are, but there's still snow in them. Okay? It's not because they necessarily get more snow. It's just that it's still cold on the mountaintops. Okay? Because they're much higher up. The temperature decreases about 6.5 degrees Celsius for every 1,000 meters up you go. Okay? Our altitude here is right around 1,100 meters above sea level. Okay? It's a fairly high altitude. right? If you go into the mountains, obviously it gets higher and higher. Okay? Now this picture here, this is of Mount Robson, okay, which is the highest peak in the Canadian Rockies. And it's a backpacking trip my father and I did a very long time ago, before you were born, probably. Okay? But on this particular day, we started at about 1,600 meters worth of altitude. It was about 14 degrees and it was raining. And we started climbing into this pass towards essentially this glacier. Okay? As we ascended, the temperature continued to decrease. And by the time we had gotten to about 2,500 meters, it was snowing. Okay? It was still raining down at our campsite. It never snowed there, right? But when we got back up to here, the temperature had dropped, okay, almost 10 degrees, and it was snowing. Okay? So altitude definitely affects temperature. Okay? There were people up on who were doing an ascent that day who were up on the top, and it was a blizzard, -20. Okay, and blowing like just horrible winds and stuff like that. Okay, very dangerous conditions to climb in, right? But they were much, much higher. Right, the top of Mount Robson's, I can't remember now, it's almost 20,000 feet. Okay, it's quite high, right? So there was much, much colder up there. So the higher up you go, the colder it's going to get. So altitude generally affects your temperature. Okay. Distribution of land and sea. Okay? How close you are to an ocean can have great effects on your climate. Okay? First off, obviously an ocean can be, but not always, be a huge input of moisture. Okay? That's not always true. Okay? There are places that are right on the ocean that are very, very dry. Okay? But it can be a place where a lot of moisture can come from. What it always is a source of energy. The ocean, obviously, is made of water. Okay? Made of water. And water has this really cool ability to retain huge amounts of energy. Okay? And so if you live next to it, the temperature of the air can start to drop. But because the ocean is there and the ocean holds so much energy, the second law of thermodynamics says that energy will go from the ocean, which is warm, to the air, which is colder, and it'll bring the temperature of the air back up, and it'll actually regulate your temperature and not allow the temperature to fluctuate wildly. Okay? So here in Okotoks and in Alberta, our temperature does tend to fluctuate wildly from winter to summer. But if you go to Vancouver or Victoria, which are almost the same latitude as we are, same distance from the equator, their temperature doesn't fluctuate like that. Okay? If you're in Victoria, it very rarely drops below freezing. And that's because they're surrounded and very close to the ocean. Okay? So if something comes through and the air temperature tries to drop, energy will flow from the ocean to the air and keep the air temperature regulated. Everybody all right with that? Now it depends on, being close to the ocean isn't always going to guarantee a regulated climate, but it can. It can also cause a very irregulated climate. You go to the East Coast, and the opposite is true. Okay? You go to Newfoundland and Labrador, okay, and places like that, they get horrible winters, okay? Big fluctuations in temperature and huge amounts of snow, right? And it's because the ocean currents, which is number 4, are different. Okay? Here, on the west coast of Canada, you have what's called the subarctic current, right? So it's a cool water current, but it's not a cold water current, right? It comes out of the Pacific and kind of moves up along the coast, okay? But the temperature of the ocean is quite warm compared to over here on the east coast, where we're looking at the Labrador current and the North Atlantic current. The Labrador current comes out of the Arctic Ocean, which can freeze in the wintertime. So when this freezes in the wintertime, okay, all we get is freezing cold water moving along the coasts of Newfoundland and Labrador, okay, causing their temperatures to actually drop. And some of the bays and things like that in Newfoundland will actually freeze over. Okay? So parts of the ocean will actually freeze over in those places. Whereas you never see that over here because the water here is coming from a more kind of mid-latitude area as opposed to straight out of the Arctic. So being close to the ocean can have big effects on moisture and temperature. Okay? And It's because of where that water is coming from. All right. Other ocean currents, you may have heard of these ones. Okay. They use them on the weather all the time, El Nino and La Nina. Okay. That's a ocean current that's actually off the coast of Chile in South America. Okay. If we get a big upwelling of warm water off the coast of Chile, that's an El Nino. Okay. An El Nino is usually followed by the exact opposite, a quick inrushing of cold water to the same area. That's La Nina. That ocean current can affect global temperatures. Okay? Even though it's really, really far away from us, it can cause us to have a really mild winter or a really horrible winter, okay? Depending on what's going on, because it can actually drop the ocean temperature by a couple of degrees. Now I know you're thinking a couple of degrees doesn't seem like much, but when you're talking about that much water, that's a lot of energy. Okay? For that much water, all the water on Earth, to cool by a couple of degrees Celsius represents a massive loss of energy. Okay? All right, so the first three are probably the most important, okay? Ocean currents also pretty important, but the first three are probably the most important ones. Okay. Okay. Now, distribution of mountain barriers is hugely important for us. It isn't important for everybody because not everybody has mountain barriers. Okay? But mountain barriers are probably, other than latitude, the single largest factor affecting climate here. Okay? So, what happens with all mountain barriers, in particular here, is that you have warm, moist air coming in for us off the ocean. Okay, so off the Pacific, coming in through BC, okay, is all this warm, moist air, because that's the way air moves from the west to the east. Okay, at least here it does. Okay, so it comes in like this, and it hits the mountains, and it gets forced up and over, because obviously it can't just go through them. Right? So as it gets forced up and over, it starts to cool down. And as it cools down, all the moisture that's in it condenses and falls as rain and snow on what we call the windward side of the mountains, which is why in BC, especially on the coast of BC, we see a temperate rainforest. Okay? Huge trees, much different than what grow here, okay? And much more moisture, much heavier rains. Okay? I don't know if anyone's watched that show, The Highway Through Hell, the tow show about the Coca-Cola Highway and how much moisture and precipitation stuff they get there. Like, it's crazy, way more than we get here. Okay? And that's because they're on this side of the continental divide of the Rockies. So all the moisture falls on that side. Well, by the time that air gets up to the top of the mountains, it's now cold and dry. Because it's lost all of its moisture and it's pushed up. We know that altitude affects temperature, so as it gets pushed up, it gets colder and colder. Well, now that cold air is heavy, because cold air is heavier than hot air, right? So it naturally comes rushing down the mountainsides on what we call the leeward side. Okay? As it descends, there's this upslope effect, okay, that happens. And this upslope effect is caused a bit by the friction of the air going down the mountainsides. Okay? So it's picking up kinetic energy because it's falling down the mountains. Okay? And that's causing it to actually heat up. Okay? So as it starts to heat up, running down this mountainside, you now get hot or warm, dry air coming down off the mountains at high speed, headed east. What do we call that? A Chinook. That's the thing Leonardo DiCaprio thought was climate change. Okay? This is how it happens. Okay? We get Chinooks all the time. And it's because we're close to a mountain range. Chinook is a very localized effect. Okay? They get a similar effect in certain places in the Himalayas, okay? And certain places in the Andes, I believe, down in South America. But it's a very localized phenomenon, and it's called by different names depending on where you go. Okay? But if you go, let's say, to Ontario even, and you start talking about a Chinook, people look at you and they're like, a what? Because they have no experience with that. It's a very local thing. Okay? That's why Leonardo DiCaprio didn't know about it. Okay? He just thought the world was coming to an end because climate was changing. Okay? Climate does not a climate change, it's a weather change. Okay? Chinooks happen, but people don't know about them. Okay? They don't understand what they are because it's not something that happens everywhere. Okay? It happens here. It happens very intensely here, okay? But it doesn't happen everywhere. All right, so what this causes is obviously Chinooks, but it also causes what we call a rain shadow. Okay? All the rain falls on this side, and you got nothing but dry on the other side, and that's why in BC there's forest, and on this side of the mountains there's prairie. Okay? In a lot of places it goes from forest to desert. You can see this actually, how many people have been to Hawaii? Okay? If you've been to Hawaii, I don't know if you've noticed this, but like one side of the island is like jungle, and the other side is like barren rock. Okay? On basically every island. Because the volcanoes are so tall that moisture gets pushed up and over the volcano, it all falls on the one side, and there's nothing left on the other. And it's all desert on the other side. Okay? Same idea, rain shadow, desert. Utah, Nevada, and Arizona are a rain shadow. Okay? The Gobi Desert in Asia is a rain shadow of the Himalayas. Okay? It's a high altitude desert, but it's very dry. Okay? And that's just all caused by this rain shadow effect. So the presence of mountain barriers can be a big effect on climate. If I go to Manitoba, I don't see that. They don't have mountains there. Okay? It's all Canadian Shield. It's much different. Okay? They don't get the rain shadow effect like we do. Okay? BC gets the rain shadow effect because they're on the good side, the rainy side. We get the rain shadow effect on the dry side. Okay. All right, questions about mountain barriers? Okay. Pattern of prevailing winds. So where you are on Earth determines what your prevailing winds are. For us, our prevailing winds are out of the southwest. Okay? Since our winds typically come from that direction, and only that direction, I mean, rarely we get it from a different direction, okay? But they tend to bring the same kind of weather. Okay, so your prevailing winds can determine your weather because they're typically bringing you the same type of air patterns on a regular basis. Now again, in Alberta, we know that that can change pretty rapidly, okay? And we can get these quick changes in pressure that cause changes in wind direction. So what happens here in kind of North America is right here is an area that always has low atmospheric pressure. Okay? Meteorologists call it the mother low. Okay? Because low pressure areas will spin off of it. Okay? Around a low pressure area, air tends to rotate clockwise, like this. Okay? And so what happens is low pressure, high moisture laden air masses will spin off of this mother low and they'll start heading this way. Okay? Right here is an area that's typically high pressure. Sorry, I drew that in the wrong spot. Right here is typically an area that's high pressure. Okay? High pressure areas tend to be clear skies and dry and often cold. This one is called the Siberian high. Okay? Rotation around a high is the opposite direction. Okay? So around the low, it was clockwise. Around the high, it's counterclockwise. Okay? If these things get spinning at the same time, they will throw two different types of air masses at each other. And given this rotation, when they start to interact, where do they go? Right through Alberta. Okay? This is why we're the tornado alley of Canada. Okay? When these things interact in the summer, they can produce really unstable weather conditions leading to massive thunderstorms and hail and tornadoes and things like that. A similar set of conditions happens here in the United States. You can see there's this, it's almost the same corridor. Okay? Tornado alley is kind of one big corridor. Okay? So in the wintertime, this is when we get the big blizzards, okay, where we get that massive change in weather and it suddenly gets really cold and we get just a huge dump of snow. Okay? It's the same thing, but it's just happening in colder conditions. Okay? That heavy moisture-laden air mass hits a really cold air mass and causes all that moisture to condense and fall as snow, okay, and move right down the center of Alberta. Okay? And the mountains tend to channel that right through us. Okay? Sort of make sense? So depending on where you are, being close to a center of low pressure or high pressure, okay, can affect your weather. If I live here, okay, this is going to be typically cloudy, rainy, and we know like the west coast of Canada, especially up in here, okay, it's like Prince Rupert and places like those are the wettest places in Canada. Okay, tons and tons of rain. Okay? Whereas here, these are the prairie provinces, some of the driest parts. Okay, here some of the coldest and driest parts, just because of being underneath that high pressure area all the time. Okay. All right, so those are the factors that affect climate. What you're going to be asked to do in this activity that we're going to start, as well as on a test, is this. I give you a map. And on there I mark a spot. And it would be someplace you'd be familiar with, like I'd pick a Canadian city. Okay? And I would ask you, describe what the climate of this city would be like based on the factors that affect climate. So if I picked Okotoks, okay, you would probably talk about what 3 climate factors? No, not components, factors. Latitude, altitude, mountain barriers. Okay, you say these are the 3 biggest factors affecting the climate in Okotoks. Here's how they affect the climate and what the climate would be like. Okay, that's what you'd be expected to do. All right, if I picked Victoria, okay, it'd be completely different, right? I mean, you could still say latitude, altitude, and mountain barriers, or you could say latitude, altitude, and proximity to the ocean. Okay? As long as you make an explanation as to how those 3 factors interact and what they're going to make the climate like, you're good. So that's what you'd be expected to do. Does that make sense? So we have to know the 4 components of climate, so we can talk about them, and how the factors make them what they are. So being close to the ocean regulates your temperature, can cause more precipitation, okay, and have your prevailing winds coming from a certain direction, okay, stuff like that. Okay, we talk about them that way. All right, climatograms. Okay, climatograms are a visual reference of the climate of an area, not containing all of the information, okay, just showing temperature and precipitation, okay, over the course of the year. From temperature and precipitation, we can discern a number of things. Okay? We can kind of figure out where on Earth this place might be, okay, based on what its climatogram looks like. So this first one is showing us a tropical rainforest. Okay? It's in New Guinea, which is basically sits right on the equator. Right? The green line represents the temperature of this area. Okay? So the temperature of this area, according to the graph, sits right on about 26 degrees Celsius all year long. Okay? If I see a temperature line that just does this, okay, I know I'm looking at a place that's near the equator, because near the equator, latitude doesn't really play a factor in how much sunlight you get. And how much sunlight you get affects your temperature. Okay? If I look here, this one's Anchorage, Alaska. Look at the shape. Okay? Now I'm seeing definite winter and summer. Okay? Even here in Nashville, Tennessee, which is kind of right smack in the middle between the equator and the pole, I still see that as I move away from the equator, I start to get this bell curve showing up for my temperature. Because as I move away from the equator and the Earth's tilt starts to come into play, it can affect my temperature. If I'm close to the equator, that's not the case. Okay? I'm going to get pretty much the same temperature all year long. Okay, how wet is this place? The bars represent our precipitation.
It's moist.
Mm-hmm. It's really moist, actually. Okay? If we're looking at this here, guys, its wettest month is 33 centimeters, not millimeters, centimeters of rain. That's a foot. Okay, a foot of rain in a month. Right? To give you an idea, in 2013, when we had the big floods, okay, we got 70 millimeters of rain. That's 7 centimeters in less than a week. Okay, and we got massive flooding. Right? That's down here. Okay, their driest month is more than that. Okay, now typically in June, we're going to get somewhere in the neighborhood of this much rain in June. Okay, so about their driest month is our wettest month. much, much different. So imagine the conditions here, okay? Almost constant flooding in the tropical rainforest. Right? Getting a foot of rain in a month is kind of a big deal. Right? If we ever got a foot of rain in 1 month, we'd have to build an ark. Right? That's what we'd be looking at. All right, now, in Nashville, Tennessee, obviously we got a temperature curve here, but looking at its location, we know it's still fairly temperate. Okay? There's no hard winter. The coldest month is still above 0. Okay? So coldest month, we're looking at like 5 degrees Celsius. Okay? So not too bad. Hottest month, 28. That's pretty warm, right? And precipitation is fairly uniform at around 12 centimeters, between 8 and 12 centimeters of rain in a month, right? That's why Nashville, Tennessee is in very much a deciduous forest kind of place, okay? You get a forest like that growing because you get constant inputs of rain and no hard winter, right? If you look at a place like Anchorage, Alaska, okay, it's much colder, okay? Down coldest month is like -10, okay? And look at the precipitation, right? It's pretty dry there, right? You got this little blip here where they get kind of most of their precipitation in August, September, October, and then the rest of the time it's less than 5 millimeters of rain. Okay? So it's a pretty dry place. Everybody all right with that? Okay. If we were to draw Calgary, okay, onto one of these, right, Calgary would look, the temperature line would be close to that. And probably be more like this. Okay, something like that. Okay. The further away from the equator you get, the steeper the curve gets and the lower on the graph it'll go. Okay, that sort of makes sense, everybody? So the lower it goes, okay, and then kind of steeper it gets. And then our precipitation lines, okay, would go probably something like this. Maybe not that high. But. Okay. Ours typically looks like that. Okay, June and July are significantly taller than the rest. Okay, what if I had a temperature curve that looked like this?
We would use around January, February, March, April, so our spring and our winter would be, or their spring, winter for us would be their warmest and coldest would be our summer.
Right, so where on earth is this?
Probably Alaska. No, Australia.
Australia, yeah. Okay, anywhere in the southern hemisphere. Okay, the bell curve is reversed. Okay, so if you're in the southern hemisphere, okay, the bell curve gets reversed because your winter is our summer. Okay, because the tilt is opposite, right? Okay, they're tilted toward the sun when we're tilted away from it. Okay. Okay. So I've kind of already gone through this stuff with you, so we're just going to skip that, and we're going to look at the next thing here. But I'm going to give you guys about a 5-minute break here because I've been talking steady. Okay, so I'm going to give you about a 5-minute break. I'm going to grab the Chromebooks, okay, and bring them out here, and you guys can grab those in a couple minutes. But let's say 9:36. Okay.